Welcome. You know, the algorithms that are changing our world, they often start with a surprisingly simple goal, just teaching a computer how to make an educated guess. In this series, we are going to pull back the curtain on the math behind machine learning. And it all starts right here with something called linear regression. So at its very core, what is machine learning all about? Well, it's really about prediction. It's about using the stuff we already know to make a really smart guess about something we don't know. So the real question is, how do we actually teach a computer to make that leap?
And the answer, you're not going to believe this, begins with something you almost definitely learned back in middle school. A simple, straight line. Yeah, that's right. The foundation for some of the most complex AI today starts with something you probably plotted on a piece of graph paper. It's just a perfect example of how elegant the core ideas in this field really are.
Okay, before we even touch a single equation, let's just use our eyes for a minute. The intuition here is super powerful.
So, let's use a classic example. Imagine we're trying to predict house prices. We've got a bunch of data on houses that have already sold. We know how big they are, we'll put that on the x-axis, and we know how much they sold for, and that'll be our y-axis. When we put all those dots on a chart, you can already start to see a pattern taking shape. Just looking at these dots, you can probably already imagine a line kind of slicing right through them, can't you? A line that captures that general trend, as the size of a house goes up, its price tends to go up too. Our brain just does this automatically. The whole goal of linear regression is to teach a computer how to find the absolute best version of that line.
Okay, so our eyes are pretty good at eyeballing a line that fits, but how does a machine do it? This is where we have to translate that visual intuition into the precise language of mathematics.
In machine learning, they have a formal name for this prediction-making tool. It's called the hypothesis function. Now that might sound a little complicated, but for linear regression, it's something you're already very familiar with. It's just the equation for a straight line.
And here it is, an equation that should look pretty familiar from your algebra days. We say y hat, and that little hat on top just means it's a prediction, equals w times x plus b. This simple formula is the entire engine of our model. The best way to think about w and b is as two control knobs for our line. W is the weight, which you might remember as the slope. This knob controls the steepness, the angle of the line. For our houses, it basically decides how much the price goes up for every extra square foot. Then you have b, which is the bias, or the y-intercept. This knob sets the line's starting point. It's like a base price for a house, even if it had zero size. By just tuning these two knobs, we can draw literally any straight line you could imagine.
So we have an infinite number of possible lines we can draw, just by turning our y and b knobs. How in the world does the machine know when it has found the right one? How does it measure what makes a line good?
Well, the core idea is actually pretty simple. The best line is the one with the smallest total error. The entire learning process is really just an automated search for the perfect W and B values that get our prediction line as close as possible to all the real data points. And how do we measure that error? It's really straightforward. For any single house in our data, we first look at its actual price, the real dot. Then we look at what price our line predicts for a house of that exact same size. That vertical distance between the real dot and the point on our line, that's the error for that one prediction. Our model was off by that much.
Now, to get the total error, we obviously need to add up all those little individual errors from all of our data points. The function that does this for us is called the loss function. It gives us one single number that tells us exactly how badly our model is doing. For linear regression, the standard approach is to use something called squared error.
So why do we square it? Why not just add up the distances? Well, there are two really clever reasons. First, it gets rid of any negative numbers. A prediction can be too high or too low, but we only care about the size of the mistake, not the direction. And second, and this is key, squaring the error means that bigger mistakes get penalized way more heavily than smaller ones. A line that is way off on just one point will get a much higher total error, which really pushes the model to fix it.
Okay, so a line that fits data. It seems simple, right? But the reason we start here, the reason this is so important, is because this simple model is essentially the hello world of machine learning. It introduces all the big ideas.
By understanding linear regression, you're actually learning the fundamental playbook of machine learning. Think about it. We have a model defined by parameters, our W and B. We have a loss function to measure its error. And we have the goal of optimization. which is just the automated process of finding the best possible parameters. These concepts, they're the bedrock for pretty much everything that comes next.
And here is the real payoff. This entire process, taking an input X, multiplying it by a weight W, adding a bias B, is exactly, and I mean exactly, what a single neuron in a neural network does. So linear regression isn't just some old statistical tool, it's the simplest neural network you can possibly build. By mastering this, you've already taken your first real step into the world of deep learning.
This all brings us to the final, crucial piece of the puzzle. We know we need to minimize the error by finding the best W and B, but we haven't actually talked about how the machine performs that search.
We know our goal, right? We want to find that perfect combination of way and B that gives us the lowest possible value from our loss function. But how do we systematically search for it? I mean, we can't just try random numbers forever. We need an intelligent strategy.
And that strategy requires two things, a map and a compass. In the world of machine learning, our map is something called a cost function, which plots out the error for every possible line we could draw. And our compass is an incredible algorithm called gradient descent, which always points us downhill toward the lowest possible error. We'll explore exactly how that works in our next explainer. I'll see you there.